All right, welcome everyone to the penultimate meeting of the GOCC this year. We're very happy to have Siddharth Kannan, who's going to be talking about generating functions in algebraic geometry and sums over trees. Before he starts, let me just remind everyone of our community statement, which says that we are all learning, everyone has something to contribute, and no one has all the answers. Okay, sorry, take it away.
Yeah. Thanks, Sarah, for the introduction and the invitation to speak here. So two things. Like one, I got the title of my talk from a paper of Yuri Manin. I just find it to be a very pleasing title, and it's a really good paper too. It's where I learned a lot of these ideas. And two, I can't really monitor the chat, so please ask questions, but just kind of unmute yourself and interrupt. And I encourage questions any type of question, even sort of maybe especially clarifying questions about terminology that I use that you might not have heard before. So, okay. So I want to start with sort of an extended warm-up, sort of an enumerative combinatorial problem. So throughout this talk, trees are always going to be finite and connected. So a tree is a graph with no cycles. And we're going to say a tree is stable if it doesn't have any degree 2 vertices. And I'll sort of use both degree and valence to mean the same thing. It's like the number of edges coming out of a vertex. And a leaf of a tree is a vertex of degree 1. So an n-marked stable tree is a stable tree T together with a bijection from its leaves to the integers from 1 through n. So L of T is going to denote the leaves of the tree. So in particular, an n-marked stable tree has exactly n leaves. So let's let gamma 0 n denote the set of isomorphism classes of n-marked stable trees. The 0 here is because this is part of sort of a larger family of sets where the 0 is the genus of the graph. So these are genus 0 graphs, but all of our graphs are going to be genus 0 today. So here's an example. This is gamma 0, 4. There are four marked stable trees up to isomorphism. And the goal of sort of the extended warm-up, which is like the first part of my talk, is just computing the sizes of these sets for all n. So some enumerative problem. So gamma 0, 1 is empty. You can't have a tree with one. You can't have a stable tree with one leaf. I mean, you can't even have a tree with one leaf, right? So 0. Gamma 0, 2, there's exactly one stable tree with 2 leaves. It's like an edge connecting 2 vertices, and the 2 vertices are the 2 leaves. Then you can verify that gamma 0, 3 is also just one tree. It's like a star with 3 leaves. And I have gamma 0, 4 here for you. So there's 4 of those, and then the sequence continues. We want to figure out how to compute these numbers. So what is the interest in this problem? So there's many interpretations of the size of this set, but I'll just give you sort of 3. So for me, it's like the number of cells of this tropical moduli space of genus 0 n-marked tropical curve. So this is some generalized, or this is really a simplicial complex, and this is just the number of cells of the simplicial complex, and maybe off by 1. Is also the number of cells of the Bergman complex of the graphic matroid associated to a complete graph with n-1 vertices. And the connection between 1 and 2 is sort of due to Ardila and Cliven's. Sometimes people call this space number 1 tree space. So it's like the number of cells of tree space, and it's the Bergman complex. It's sort of the fine subdivision of the Bergman complex, if you're sort of up on Bergman complexes. And then a third interpretation is that it's the number of boundary strata of this Deligne-Mumford compactification of the moduli space of genus 0 and marked curves, also sort of off by 1. So like this is M0n is like some space. It's pretty concrete. It's like configurations of endpoints on the projective line. So P1 is like the Riemann sphere, or the projective line over the complex numbers. So it's really a sphere with a complex structure. And conf n means like n distinct ordered points on P1. And then we sort of take the quotient by the automorphism group of P1, which is like Mobius transformations. So this is sometimes called the moduli space of n marked genus 0 curves. And it's not compact because sort of like you don't know what to do when points approach each other. And one compactification is provided by this Deligne-Mumford space M0n bar, and I'll sort of talk more about that later. But gamma 0n, sort of the strata at infinity of this compactification correspond to graphs in gamma 0n. This is like 3 interpretations of this number, and there are sort of many more. Like the sequence is on the OEIS, and there's a lot more sort of interpretations that I'm less familiar with. So like let's put all this into a generating function. So let's let n of x be the exponential generating function for the sizes of these sets. So yeah, so we like computed the first few. I think that was a mistake. Yeah, okay, this should be 4. Sorry, but yeah, so we computed the first few numbers. So let's calculate this generating function. Any questions so far?
One question on this generating function: why the n factorial?
It's just going to be cleaner for what I'm going to do today, but it's maybe a better answer is that this is a shadow of like a symmetric function. So you could think of like the Sn representations defined by these sets, like the permutation representations, and this would be like the rank of that symmetric function, if that makes sense.
Okay, thank you.
Yeah, okay, so let's calculate this thing. There's probably many ways to calculate this, but I'm just going to do one sort of fun way that I like. So we're going to define sort of I of t to be the set of internal vertices of a tree T. So by internal, I mean like it's not a leaf. So like the non-leaf vertices. So the vertices that don't have degree 1. And I'm going to let gamma 0 n upper v denote the set of pairs T comma v, where you have a tree together with a choice of internal vertex. And same for gamma 0 n e. So it's like pairs consisting of a choice of tree and a choice of internal edge. So like internal edge means like an edge that's not adjacent to a leaf vertex. And I'm going to let n sub v of x be the exponential generating function for the sizes of these gamma 0 n v's. And then n sub e of x is going to be the generating function for these gamma 0 n e's. Right. So this is like summing, this is, I could have just written this as the coefficient of x to the n over n factorial here is the size of gamma 0 n upper e. And analogously with this vertex generating function. So these are 2 auxiliary generating functions that are going to be easier to compute. And we're going to use this to compute our original generating function. So sorry for all the notation, but hopefully we can keep track of it. So the sort of key observation is that n of x, is sort of the original generating function I wanted to compute, is n sub v of x minus n sub e of x. And this is just the observation that a tree has Euler characteristic 1. Like it always has one more vertex than like the number of edges. So when I do the subtraction, like I'll end up counting the number of trees with n leaves as the coefficient for x to the n over n factorial. Yeah. And you might quibble with me and say like, okay, but this is only internal vertices and this is only internal edges, but the set of internal vertices and internal edges like also forms a tree, and that still is going to have Euler characteristic 1. Are there any questions about this equation? Okay, great. So yeah, let's use this to calculate this n sub x. So I'm gonna maybe talk about like calculating this term in a little bit of detail, and then I'm gonna wave my hands at this term. So this n sub e of x, so like let's consider the derivative of n of x. So recall n of x was the generating function for gamma 0 n, so the derivative ends up being the generating function for gamma 0 n plus 1. It just shifts everything by 1. And let's momentarily think about gamma 0 n plus 1 as like parametrizing trees marked by 0 through n, instead of 1 through n plus 1. So like the question is like, what happens if I square this derivative generating function? Like what is the coefficient of x to the d over d factorial? And this is like some exercise that you can just do, like when you multiply two exponential generating functions, you get this sum where you like sort of take one term of degree k and one term of degree d minus k, and then you have to like weight by this binomial coefficient. But we can think about this coefficient as like the size of like some set. It's the size of this disjoint union from k equals 0 to d, where you have like a k subset of d that's like this binomial coefficient. Then a tree with k plus 1 leaves, and then a tree with d minus k plus 1 leaves. That's what this coefficient is counting. So you can think about this, squaring this generating function, I get another generating function that's like counting some sets. I mean, it's like these some seemingly random sets here.
Wait, sorry, did you say why you're squaring the generating function?
No, I did not say why I'm squaring it. We'll see that sort of momentarily.
Okay, thanks.
Second question, I'm not familiar with, why is my product symbol upside down?
Oh, this is a disjoint union. Right?
Okay, got it.
Yeah, thanks for the questions. Okay, so let's observe something. So if I take this seemingly random set, I actually can map it to gamma 0 DE. So recall this is like D marked trees together with a choice of edge. So like how does this go? Like let's momentarily ignore this K subset of D. Let's just think about these two factors. So I have a 0 through K marked tree here, and a 0 through D minus K marked tree here. Well, I can just sort of glue at the two leaves marked by 0 and like smooth the resulting degree 2 vertex. And then I have a tree with D leaves, and then I also have sort of a natural choice of edge, right? The edge that sort of came from gluing these two like half edges together. And then like, okay, the choice of K subset of D sort of determines the reordering of the leaves. Like the number of ways to combine these two ordered sets, like one of size K and one of size D minus K into like one big ordered set is exactly this binomial coefficient. It's determined by a choice of K subset. So and then this is 2 to 1 because there's some involution of this whole set that preserves this map. So this is why we squared the generating function, because there's a tight relationship between squaring this derivative and then like this sort of auxiliary generating function that I defined, and this is the tight relationship. So if I square the derivative and I divide by 2, I get back my edge generating function. So okay, so that's like, so I hope that made some sense. So like that's how you calculate this n sub e generating function. And now I want to say something about calculating this n sub v generating function, and it's going to be even more informal than the previous calculation. So now this n sub v generating function is like I see a tree together with like a choice of internal vertex. And this choice sort of determines a natural decomposition of my tree. Like I sort of take that vertex and I sort of prune sort of around it. So I get sort of a tree with one internal edge, and then I get a bunch of other trees. And like the way I've labeled these leaves is supposed to like indicate like gluing. So like Y gets glued to Y, X gets mapped to X, and etc. So like the point is that like, so if I define this, it says H sub X to be the generating function for trees with exactly one internal vertex, well, okay, that's like pretty easy because there's only one tree with exactly one internal vertex for all n at least 3. So that's some explicit thing. But this vertex generating function is like h of x composed with the derivative of n of x. So the point is this composition is somehow supposed to be interpreted as like an attaching operation from this picture. So I'm composing the generating function for like objects that look like this with like the generating function for rooted trees. And that's what's going on in this picture here. So like now we've calculated both n sub v of x and n sub e of x in terms of our original generating function. So if you put this together, so we had this equation, this is just the fact that the Euler characteristic of a tree is 1. And then we had these two calculations, so that we calculated n sub e of x, like semi-rigorously, and we calculated n sub v of x sort of informally, and we got this equation. And then you can take my word for it that if you take derivatives of both sides of this equality and rearrange, you get the following formula. So x minus h prime of x is composition inverse to n prime of x. And we can recall that h prime of x was sort of totally easy to calculate. It's basically an exponential. Okay, does this formula make sense? Are there any questions about this?
Could you very quickly remind me what h of x was?
Yeah. So it was the generating function for trees with exactly one internal vertex, but there's only one such tree for each n at least 3. Right, so it ends up being like e to the x minus it's like degree 0, degree 1, and degree 2 terms.
Awesome, that helps a lot. Thank you.
Yeah. So okay. Yeah. Thanks for the question. So we have this inversion formula. So now we can enumerate these numbers or enumerate these sets. So here's like the first 10 terms. So like, how did I do this? You sort of like Sage can just like invert a power series that is invertible. So you can just put in this x minus this, and you can invert it. So you can calculate these numbers. And it's on the OEIS. It's this OEIS sequence if you want to look it up. So yeah, that was sort of the warm up of the talk. And so I want to shift a little bit to talking about how this relates to something from algebraic geometry, and I'm going to focus on these for now on these moduli spaces that I referred to earlier. So recall like M0n is this configuration space of n points on P1 modulo automorphisms of P1. So two configurations are the same if they're related by an automorphism of P1, which is a Mobius transformation. And like some like some fact is that like a Mobius transformation is sort of determined by what it does to like 3 points. So you can think about this as the configuration space of n minus 3 points on P1 by just sort of choosing the orbit where the first 3 points are 0, 1, and infinity. And I'm going to do this weird thing where I'm going to just assume n is at least 3 from now on. And that's because from the sort of algebra geometric perspective, this quotient is like, I mean, it's slightly problematic if n is less than or equal to 2. Like, I mean, you can form the quotient, but it won't be like an algebraic variety. It'll be something a little bit weirder. So I think since I'm sort of scared of like stacks and stuff, I like to focus on this more concrete case where n is at least 3. But when n is at least 3, it's a pretty concrete thing. It's like the configurations of n minus 3 points on P1. But so this thing isn't compact. So like one really nice compactification is provided by algebraic geometry. It's the Stalin-Mumford compactification. And to define it sort of informally, it's like tuples. So it's a tuple consisting of a curve C and n marked points on the curve. So C is going to be like some sort of tree of P1s, by which I literally mean like take a bunch of P1s and glue them together to form some tree. and the marked points pi are sort of distinct smooth points. So the singular points of this tree are going to be where you've sort of glued two of your p1s together. So you can't choose those as your marked points. And then there's this so-called stability condition. So each irreducible component, by which I mean each bubble in your tree, supports at least 3 special points, whereas special point is like a node or a marked point. And a node, when I say node, I mean like a point at which you've like glued together 2 of your bubbles. So this is somewhat informal. Let's like look at a picture. So like here's a point of M05 bar. So it's a tree consisting of 3 P1s glued together at these nodes, and each component has at least 3 special points, right? Because these nodes also count as special points. And each point in this moduli space has an associated combinatorial object, which is the sort of the dual tree. So the dual tree is like you put down a vertex for each irreducible component, you connect them by edges for these nodes, and then you add sort of degree 1 vertices, like keeping track of the distribution of marked points. Okay, so any questions about this moduli space that I informally introduced?
Can I ask a question?
Yeah.
So you said like we need to compactify because we don't know what to do when 2 of the marked points clash. Should I think about this bubble as like popping out where they would have touched?
Exactly.
Like that?
Yeah,
Okay.
That's exactly what's going on. Yeah, okay, so now we can like chop up our space based on like the underlying tree. So given a tree, an n-mark stable tree T, we like let M sub T be the locus of curves that have that dual tree. So like this M0 n bar is like a disjoint union over these trees of these like M sub T's. So it's just like, you know, you take every curve here and you put it in a bucket corresponding to which underlying dual tree it has. So this is some stratification. And then the other cool fact is that if I look at one of these buckets, like the bucket corresponding to a fixed tree, that decomposes a product over the internal vertices of like these open moduli spaces. So this is M0 comma valence of V. So the valence is the same as degree. So here's an example. So if I look at this bucket in M05 bar corresponding to this tree, it's like an M03 times an M03 times an M03 for each of these internal vertices. And again, I've labeled, so I've chopped up my tree here, but I've like labeled the new sort of leaves based on how they should be glued together to form this tree. So this I find this to be a very pleasing geometric description of this space. Like it's somehow like totally controlled by these open moduli spaces and tree combinatorics. Okay, so now we can use this idea to sort of compute the topological Euler characteristic. So the Euler characteristic of the space is now going to be a sum over all trees with n marked leaves of the Euler characteristics of these buckets. So this on the previous slide, this was M sub T. So sorry for the notation change. And then because Euler characteristic, multiplies across products, and I know that M sub T is like a product over the vertices of the tree, I now have this equation where this Euler characteristic, the sum over trees, and then a product over the internal vertices of the tree of some sort of weight corresponding to the open moduli space. And it's actually like quite easy to calculate the Euler characteristic of the open moduli space. So there's a forgetful map of where you like sort of forget one of the marked points, and the fibers are always like P1 minus n points. So you can kind of use that to calculate this Euler characteristic of the open space. It ends up being like basically n minus 3 factorial, up to this sign. So like this sum now is like really combinatorial. It's like a sum over all trees a product over the vertices of the trees of like basically the degree minus 3 factorial up to a sign. Any questions about this? Okay, great. So now we can introduce generating functions for Euler characteristics. So like mu of x is going to be the generating function for the open Euler characteristic. And then mu bar of x is going to be the generating function for the compact Euler characteristic, or by which I mean the Euler characteristic of the compactification. And in fact, like totally the same logic as before, the same logic that we used to calculate the generating function enumerating these trees also allows us to calculate these generating functions, or at least say that x minus mu prime of x is inverse to x plus mu bar prime of x under composition. So okay, so like maybe this was first due to Manin, maybe in the paper that I took the title of this talk from. And then Getzler sort of does this SN equivariantly in his cyclic operads paper. It's like I said, it's sort of easy to calculate these numbers, or like we know how to calculate these numbers pretty concretely, because this is, and so because this ends up being like n minus 3 factorial times minus 1 to the n plus 1, we have a really explicit description of what this term is. Like it's 2x minus 1 plus x times log 1 plus x. So this generating function we have a closed form for, so that allows us to solve for this generating function and hence this generating function. So you can use this, so you can use this to calculate these numbers. So Manin also used this to give an asymptotic formula for this topological Euler characteristic. So it's pretty big as n gets large. This is also on the OEIS. Let me also say that this M0n bar doesn't have any odd homology or cohomology. So the Euler characteristic is really just like all of the cohomology that the space has. So I view this asymptotic formula as saying like it really has a lot of cohomology as n gets large. Okay, so I'm gonna shift gears again now. So are there any questions about this M0n bar section of the talk, or whatever?
You sort of hinted at these are like shadows of symmetric functions, and then you said that there's like a SN equivariant story. What is the...
Yeah, great question. So replace this with like the Frobenius characteristic of the cohomology of M0n, like the alternating sum of the Frobenius characteristic, so the SN equivariant Euler characteristic.
Yeah.
So that's a symmetric function for each n, and like sum that up, and then do the same thing here. And then the formula is P1 minus the P1 derivative of the analog of this is plethism inverse to P1 plus the P1 derivative of the symmetric function analog of this. So x gets replaced with P1 here.
Mm-hmm.
So this is a consequence of just applying the rank homomorphism to that the SN equivariant identity due to Getzler.
Cool. Okay, thanks.
Yeah, the SN equivariant story is quite beautiful and I think worth looking into. Okay, so let me shift gears now and maybe talk a little bit more about like how some original work. So I want to talk about applying these ideas to these other moduli spaces called moduli spaces of relative stable maps. So the input data for one of these moduli spaces is you need like a vector of integers that sums to 0. And so given one of these vectors, we're going to define a moduli space K of X, and it's going to be like a moduli space of maps from P1 with n marked points to P1 relative to 0 and infinity. And the preimage of 0 has to be like those marked points corresponding to the positive entries of X. And the preimage of infinity is like, okay, this should be less than 0. Is the marked points corresponding to negative entries of X? So sorry for the typo. And we're going to require that f ramify at the ith marked point with degree given by the absolute value of xi. So like anytime you have like a map of Riemann surfaces, like locally around each point, it looks like z maps to z to the n for some n. So this condition is saying that around the ith marked point, it should look like z maps to z to the absolute value of xi. So that's one way of understanding this ramification condition. And then all of this data is like taken up to isomorphism, where an isomorphism of two of these objects is like a commuting square of maps. So this is like a new moduli space. And so far we're only looking at maps from smooth curves to smooth curves, like so like a smooth, P1 to P1. And it's sort of important, like to have a non-empty space here, it's important that the sum of these entries is 0, because it's like some fact that like if you look over any point up here and you add up the ramification indices in the fibers, that's like a constant, which is called the degree of the map. And basically any of these maps is like almost a covering map, except for these ramification points. It's like a branched covering. So like, okay, so the first observation is that actually this isn't so complicated. It's actually just M0n again, secretly. And that's because like the map is really determined by sort of the locations of the zeros and poles and like their orders. So as soon as I tell you where the zeros are and where the poles are and like what the ramification index at each of those points is, that like determines the map. So like this moduli space is just and marked points on P1 up to automorphisms of P1. But there's a compactification of this space that sort of uses the interpretation of the points as maps. And this compactification allows the source and the target of the morphism to degenerate simultaneously. So we're going to have some moduli space where the sort of the limiting the points at infinity correspond to sort of singular objects, but now it's going to be sort of maps between singular objects. So this is some different compactification of M0n, different from M0n bar, and it's called the moduli space of relative stable maps to P1. Now, I'm about to tell you in slightly more detail what it is. So like in general, we're going to be looking at maps from X to Y, and X is going to have n marked points called P1 through Pn, and Y is going to have 2 marked points, sort of suggestively called 0 and infinity. And X is going to be a tree of P1s as before, but Y is also going to be a tree of P1s, but like a restricted type of tree. It can only be like a chain. So the dual graph is always a path. So here's like a cartoon of like what one of these objects might look like. So like the source here is like some tree, the target is a path. These 2 marked points, 0 and infinity, are required to be on the 2 extreme components of the path. And then I'm still going to require that the preimage of 0 is like the positive marked points, and the preimage of infinity is the negative marked points. And now, you got to say some stuff about nodes. So like the preimage of a node downstairs has to be a union of nodes upstairs. And also a node will always map to a node basically for topological reasons. So you need to say something about ramification at nodes. So there's a well-defined ramification index, whatever that means. Isomorphisms are commuting squares as before. And there's a stability condition, which is combinatorial. So every component downstairs is going to have a bunch of components upstairs. And at least one of those components upstairs has to have at least 3 special points. So like maybe you remember before we wanted all of our components to have at least 3 special points, but now it's sort of a little bit different. So this component has this component in its preimage with just 2 special points, but that's okay because it also has this component which has 3 special points, the node P4 and P5. And K bar of X is going to be the moduli space of these objects, like these morphisms from these sort of degenerate, these trees of P1s to chains of P1s. Are there any questions about this? I know this was sort of a lot on the slide.
I guess
Okay.
I do have a question. So when we're trying to find the pre-images of our nodes, like the picture is suggestive here where I kind of put positive points on one end of my tree, I put the negative points on the other ones, and it appears, I mean, this tree is so small. Like the pre-image of the node is all of the other nodes. But is this in general how I should be thinking about it? I kind of set up my tree planarly in that way and look for breakpoints and try to create a path in that way, or is it not that nice?
So I don't think you can generally always draw these pictures planarly. Although I don't know that I can justify that. And another thing is, you might have sort of more nodes downstairs and more sort of nodes upstairs. So here there's only one. There's only one on the target. But I could have sort of further degenerations where my target has like 1 million P1s.
Right.
But certainly, like, it's certainly the case that the pre-image of a node is always a union of nodes.
Okay. I mean, the upstairs thing, like it's a tree. Trees, I think, are fundamentally planar.
Yeah, the tree itself is definitely going to be planar. I don't know if you can always draw it in this nice way. I don't know what I really mean by draw it in this nice way. Yeah,
Okay.
Yeah, I'm not sure.
Okay, that's all I have.
Anything else? Okay. Yeah, if anything comes to mind, please ask. So like, let me give you some context for like why, we might care about these spaces. So like there's these things called Gromov-Witten invariants, which, where they sort of have to do with like counting maps from curves to like some target manifold. In this case, the target is P1. So these things they end up being integrals across this moduli space. And I'm being, sketchy, like, so I know you don't need to know what this means. They're integrals of something, some cohomology classes on this moduli space. And then there are also these things called genus zero double Hurwitz numbers, which are maybe more, familiar combinatorially. I mean, they're counting maps from P1 to P1 with sort of fixed ramification profiles over 0 and infinity, and sort of simple ramification everywhere else. And I just wanted to list like, a bunch of papers / authors who've worked on this stuff. And in particular, I wanted to highlight these 4 references for being like very combinatorial. So like, so these genus zero double Hurwitz numbers, they rely on this input datum of like this vector X. So it's natural to ask like, what's the structure as we vary X? Like what kind of function is it? And it turns out that it's a piecewise polynomial function. And this was first proved by Goulden, Jackson, and Vakil. And somehow they do this by expressing these Hurwitz numbers as like lattice counts in polytopes, and basically using Ehrhart theory to show that it's piecewise polynomial. And then Schadron, Shapiro, and Weinstein, they sort of like said exactly like what the chambers of polynomiality were. And then Cavalieri, Markwig, and Johnson sort of extended this to higher genus, whatever that means, using basically tropical techniques. And then there's also this work of Cavalieri, Markwig, Ranganathan on tropicalizing the moduli spaces I'm talking about today. And really a lot of the combinatorics that, I basically learned most of this from their paper. So that might be a good place to start if you're interested. And yeah, for the remainder of the talk, I want to specialize to this very particular ramification data, where there's like one positive entry, which is n, and then n negative entries, which are all -1. So, and we're going to set k bar of n to be k bar of x for this ramification data. And in general, so like k of n, the open locus inside of k bar of n is isomorphic to m0 n+1. And then K bar of n sort of admits a map to M0 n plus 1 bar, which is like a proper birational map. So it ends up being like some iterated blow up of M0 n plus 1 bar. But it's not so important for the talk. So each of these maps in K bar of n has an associated morphism of dual trees. So this is a pretty good cartoon of what these points are going to look like, because there's always going to be like one positive entry, and then the rest of the entries are going to be negative over infinity. So like, like I can just like draw the dual graph of the source and the dual graph of the target, and there'll be like a map of trees between them. So like, so like vertices will map to vertices, edges will map to edges, and leaves will map to leaves, basically because of all of like the conditions we put on this moduli space K bar of n. And there's always, they're always going to have this particular shape where sort of 0 has one preimage and infinity has the rest of the preimages. Any questions about this?
Not a question, but I guess this is the nice case where this is what I was visualizing.
Yeah. Yeah, I mean, I think every picture I actually draw of these sort of looks like this.
But yeah, presumably in this, I'm not exactly sure what led to this niceness, but generally you don't just have one positive
Yeah.
vertex.
So that this is
so you don't get a
particularly
rooted
nice
tree, and so it's much less nice.
Yeah, that's why I specialized to this ramification data. Okay, so we have this map which takes a combinatorial type of a map in K bar of n. So remember, combinatorial map means like combinatorial type means this like map of trees, and you just like take the source curve and smooth out all the degree 2 vertices. So then you will get like an n plus 1 marked stable tree. So I'm sorry about the weird indexing where there's like n here and n plus 1 here. It's important to remember that the maps here actually have n plus 1 marked points. The index n is actually referring to like the degree of the map, which is equal to the ramification index at the first marked point. So this is like some combinatorial procedure where we just we smooth out these bivalent vertices. And now we can do the same sort of game we did for M0 n bar, where we sort of put the maps in this moduli space into buckets based on which combinatorial type we have, right? So like K sub C is like, so C is supposed to be the data of a map of trees, and K sub C is like the bucket of maps that have that underlying map of trees. And then we can sort the buckets based on which n plus 1 marked stable tree we get upon doing the procedure outlined on the previous slide, like taking the source and smoothing out all the degree 2 vertices. So now if I want to calculate the Euler characteristic of this space, I now have it expressed as a sum over trees. So I have for each stable tree T with n plus 1 leaves, I have to sum all of the combinatorial types stabilizing to T, and I have to calculate the Euler characteristics of those buckets. So the key fact that I sort of want to sweep under the rug for the sake of time, so for a fixed tree with n plus 1 leaves, if I look at this sum of all of the buckets stabilizing to that tree when I smooth out bivalent vertices, this Euler characteristic ends up being something called O sub T times the Euler characteristic of M sub T. So O sub T is a combinatorial factor I'm going to define on the next slide, depending, I guess the notation suggests it should only depend on the tree T. And then this M sub T is sort of our friend from before. It's like the product over the vertices of these old moduli spaces, M0 valence of V. And we can calculate these numbers. They're like n minus 3 factorial up to a sign. So let me define these factors O sub T. So if I have an n plus 1 marked tree T, I'm going to consider it as a rooted tree by choosing the root to be the leaf labeled by 1. And this is going to induce a directed tree structure on my tree. So, okay, so here's like a 5 marked tree. So I have one leaf that's labeled by 1. And I'm just going to choose that to be my root. And I'm gonna sort of direct the edge sort of adjacent to 1, sort of away from 1. And then I'm going to direct the sort of the next level edges sort of away from this vertex. And I'm going to continue in that way. So I got a directed tree structure where sort of everything, you sort of imagine everything sort of flowing away from the root vertex 1. And then here's another example of another stable tree with 5 leaves. But now the leaf labeled 1 is over here. So if I sort of do this procedure again, I get this directed tree structure. And O sub t is going to be the number of orderings of the internal vertices which are compatible with a directed tree structure. So compatible, like the directed tree structure is giving me some partial ordering, right? Like, so like this vertex is less than this vertex, and it's also less than this vertex. So I want to count the number of ways to order these 3 vertices that's like compatible with that rule. And similarly here. So I think here it's going to be 2. Because I have to put this one first, and then I can sort of freely order these 2 because they're not comparable in this partial ordering. Whereas here it's 1 because I have 3 internal vertices and they sort of form a directed path. So this has to be first, this has to be second, and this has to be third. So that's what this O sub t factor is. So like, here's an example of calculating the Euler characteristic of K4 bar. So it's a sum over trees with 5 leaves. It's like the number of orderings of that tree as described on the previous slide times the Euler characteristic of this sort of M bucket corresponding to this tree. And okay, so you can also reorganize this by forgetting about the labelings of the non-root vertex and letting L sub t be the number of ways of labeling, but let's not worry about that too hard. So like, okay, so here's sort of the 5 sort of S4 orbits of trees here, and I've sort of drawn them with their directed tree structure as sort of, you know, forced by the location of the leaf labeled 1. And you can count the ordering, so it's like 1 for all of them except this one that was on the previous slide. So like, you know, you can freely order these 2 vertices. And then recall that the chi of M sub t is just a product over the internal vertices of like n minus 3 factorial up to a sign. So that's easy to compute. And the number of ways of labeling these to get like, you know, an actual 5 mark tree, it ends up being like 4 factorial for like the total number of ways of labeling divided by the size of the automorphism group. So that's some straightforward calculation. And then you sort of take the products of the rows, and then you add them all up and you get the Euler characteristic of the moduli space. Any questions about this? Okay, so in general, like, what does this calculation look like? So in general, I have the Euler characteristic of k bar of n. And again, I can sort of, you know, this SN quotient is just forgetting about the labelings of the leaves not marked 1. And then I have the factor corresponding to the number of ways of labeling the leaves times this ordering factor times this like product over the vertices factor. And I can reorganize this sum based on the number of internal vertices of the tree that I see here. So like, you know, I can have 1 internal vertex up to n minus 1 internal vertices. That's some calculation. And I'm going to call this quantity like the Euler characteristic of k bar n parentheses d. So d is the number of internal vertices contributing to this part of the Euler characteristic. And this is actually the Euler characteristic of some space. It's some stratum inside of k bar of n. So like all I'm doing here is I'm sort of sorting the trees based on the number of internal vertices they have. So here I have 1 internal vertex, here I have 2, and here I have 3. And I have a contribution from each of those. And the sum gives me whatever, 10, I guess, as before. Okay, so now let's define some generating function. So this nu sub d of x is going to be the exponential generating function for the contribution of trees with exactly d internal vertices to my Euler characteristic. So for example, like nu sub 1 of x is the contribution of trees with exactly one internal vertex. And that ends up, so having one internal vertex, that ends up being just the generating function for this open moduli space M0 n plus 1. And that's a calculation that is straightforward to do. So this is just, because this is like n minus 2 factorial times minus 1 to the n. So this is an explicit generating function. So in general, calculating this nu sub d of x, okay, it's like a sum over rooted trees with d internal vertices, and then there's this sort of so there's the number of ways of labeling the leaves, there's the number of orderings, and then there's this product over vertices, and then there's this so n of t is just the number of non-root leaves of t. So this is just writing this generating function as sort of a sum over all rooted stable trees with d internal vertices. It's not too important, but it sort of begs the question of like, how do you count these orderings? So there's no reason for the word ribbon here. So how to count these orderings for like a general rooted tree T. And the point I want to make is that there's going to be some recursion in this problem. So like if I take some like random rooted tree T, so I have my root labeled by 1, and then I have this directed tree structure, and I want to count the number of ways of ordering the, so if there's 1, 2, 3, 4, 5, 6 internal vertices here, how many ways are there of ordering them that's like compatible with this directed tree structure? So like we could just like, directly count, but it's maybe a little bit unwieldy. So like, let's try to find some structure. So what you can do is you can take this tree and sort of break it at this base vertex, sort of the vertex connected to the root. And then the observation is you kind of get a bunch of pictures that are like smaller versions of the same picture, right? Like these are somehow rooted trees for a smaller moduli space. And then so like here, there's only 2 internal vertices and they're connected by a directed edge. So there's only 1 ordering here. And then here there's 2 orderings because there's 3 internal vertices, and this one has to be less than these 2, but then you can order these freely. And then in general, when you want to combine a bunch of ordered sets into a big ordered set, it's like given by some multinomial coefficient. Here it's just a binomial coefficient because there's just 2 ordered sets. But here it ends up being like 5 choose 2 ways of combining these orderings. So there's 10 ways of combining. So the total number of orderings of this big tree is like the product of these 2 orderings times the number of ways of combining. So there's 20 orderings. So I just the point of this slide is the recursion in this problem. Are there any questions about this calculation? So in general, I might break, I might have like a bunch more trees down here when I do this breaking procedure, which is why I've written this as a multinomial coefficient instead of a binomial coefficient.
Sure.
Okay, so like, what is the upshot of this intuition? So recall this Euler characteristic of k bar n of d is like this, it's sum here. It's a sum over trees with exactly d internal vertices times these with these combinatorial weights basically attached, one of which is the number of orderings compatible with this directed tree structure. And this nu sub d of x is the generating function for these Euler characteristics. And the theorem is this recursive formula for these nu sub m of x. So like let's just stare at this momentarily. So this is the generating function for m vertices, and we should observe that the right hand side only depends on 1 through m minus 1. So it's a recursive formula. And let me say here, like this means the jth derivative of nu 1 of x. And then here, basically, you have like some powers of these generating functions showing up, and like everything else is basically a multinomial coefficient. is the idea. So you're summing over like, so the sum over partitions is basically like the different ways you can break up your tree, doing the sort of procedure outlined on the previous slide. But importantly, it only depends on nu1 through nu m-1. So for example, if you like plug in m equals 2 here, everything degenerates and you end up with like nu1 prime times nu1. And like I've been trying to emphasize that the nu1 calculation is very straightforward. That is the one that we have like a closed form for. So that's, you know, it's basically log 1 plus x times 1 plus x. So this the point of this theorem is that you can recursively calculate any of these generating functions. And then the third thing to keep in mind is that the Euler characteristic of the moduli space you were interested in is the sum from d equals 1 to n minus 1 of these k bar n of d's. So in particular, this formula also lets you calculate these Euler characteristics, which was maybe the thing that I was a priori interested in. Like these are sort of just like auxiliary strata that we were interested in order to calculate this Euler characteristic. Any questions about this?
I have a question that's similar to my other question, which is there a way to make this theorem like equivariant?
Yeah, no, I hope so. Like, I don't know how to. So there's some like, yeah, I would really like to see that happen, but I don't know how to do that.
Are all the like pieces, like the breaking maps and things that you had, like, are those equivariant or?
That's a good question. I don't know. I mean, so okay, I'm not like totally sure where this breaks down SN equivariantly.
Mhm.
Yeah, I mean, I've thought about it a little and I haven't been able to make it work, but certainly someone should do that.
Mhm.
Maybe it'll be me, maybe it'll be someone else.
Thanks.
Yeah, thanks for the question. So let me just show you this data. So like so the reason for comparing this m0 n plus 1 bar with k bar of n is that so they're compactifications of the same interior, right? They're both compactifications of configurations of n plus 1 points on P1, up to automorphisms. But this one is somehow like more complicated. It's like an iterated blow up of this one. So like it's natural to compare like the amount of cohomology both these spaces have. And like this one also doesn't have any odd cohomology. So this really is a measure of the total amount of cohomology. And like you already see it like, you know, like up to 8 or 9 mark points, there's like sort of a lot more for k bar of n. So that's suggestive. So yeah, let me just conclude by you know, some future posing some questions for the future. So like one thing is like so there's an asymptotic formula for this Euler characteristic. So Manin has this formula for the Euler characteristic of m0 n plus 1 bar asymptotically. I would like to see how someone work this out for k bar of n, like probably someone who's like, you know, better at like sort of generating function analysis than me. So one thing I'm pretty sure that I can show is that the quotient goes to 0. So there is more asymptotically in k bar of n. This is basically by using the sort of iterated blowup description. But you know, an actual asymptotic formula would sort of tell us how much more cohomology there is as n goes to infinity. A second thing would be like counting the boundary strata of k bar of n. So like when I talked about m0 n plus 1 bar, I started by counting the boundary strata. That was like the first 20 minutes of my talk, like counting those sets gamma 0 n. And then I talked about the Euler characteristic. But actually, I don't know how to count the boundary strata of k bar of n. Basically, there's like lots more strata that don't contribute to the Euler characteristic, which is why I can calculate the Euler characteristic, but not the number of boundary strata so far. And 3 is Sarah's question. So like, I would really like an SN equivariant formula for these Euler characteristics. You know, something maybe involving plethism. I'm not totally sure how it would look. But yeah, that would be really nice. So that's all I have. So thank you.
All right, let's thank our speaker. That was a great talk. Very interesting. Are there more questions?
I had a question. So you mentioned that sometimes like we take the combinatorial type of a map in K, or maybe it was K bar, and then sometimes you can have like two different combinatorial types that would smooth out to the same tree. Could you give an example? I wasn't sure how that would happen. Or is there, if there is a small example?
Yeah, so let's see if I have an example. It's already. Okay, yeah, so here, oh, this one's not good, because there's only one. Yeah, okay, like you could imagine maybe like moving this vertex like slightly to the right. And then you'd have to like subdivide this edge once more and then subdivide these edges to like follow the rules of being in the moduli space. But you would still have the same underlying tree upon smoothing. I hope that makes some sense. That's why
Okay.
this ordering sort of come up. Like the different orderings correspond to different types that smooth to the same tree.
Okay, thank you.
I'm wondering if you have, I mean, this is a bit abstract, but you know, we're talking about genus 0 here. What would it mean for this to not be genus 0? And you know, if that's too, I don't know, if that's just briefly, I don't want to, you know, yeah, I don't want to ask you to give a whole lecture, you know.
Yeah, so like, okay, so like let me yeah, let me just talk about this case of M0n and M0n bar.
Sure.
So
yeah.
like M0n, another way to view it is like n marked points on a genus 0 smooth curve. And it just turns out that all genus 0 smooth curves are P1. But like M1n or M2n is like n points on a genus 2 curve, like the moduli space of all of those.
Okay.
And then when you compactify, you want to let your like genus G curves degenerate. And then somehow the degenerations are controlled by genus G graphs instead of genus 0 graphs. So you might like now have cycles in your graphs. That's the rough idea.
Yeah.
But there's still like lots of cool graph combinatorics in higher genus. It's just much more complicated.
Yeah. Okay. Thank you so much for that. That's great.
One more hopefully quick question. What would be your favorite resource for learning about the SN equivariant structure on these things and the symmetric function interpretation of that identity?
That's yeah, so I guess it's so Getzler, so that the Getzler cyclic operads paper is like a place to look, but it's like a little bit hard to read if I'm being honest.
I've tried to read that paper. It's
Yeah. I'm trying to think if there's like a yeah, I guess there's also this there's this paper by Getzler and Pandra Pandey called Betty numbers of the Consavage space of stable maps or something. If you email me, I can send it to you. But like the introduction is, I think, pretty readable and like talks about this genus 0 case a little bit. That's actually where I learned this trick of like what's the trick? This trick I learned from that paper actually. So there's yeah.
I have a question that's sort of I don't know if it will make sense, but so this original sort of warm-up story that you told us had this really cool like plethistic inverse relationship between the space and its like one of its compactifications, right? Is
Yeah.
that something that you know of happening with other spaces, or is that just like by chance this space is really nice and so it happens?
Yeah, I mean, it has to do with the fact that somehow the space is totally controlled by trees. So
Mhm.
like, have you ever heard of this like Fulton McPherson space? Like the so you can, for an arbitrary variety X, you can try to compactify the space, the configuration space of endpoints in X. And Fulton and McPherson like gave some nice compactification that has like nice properties from the AG perspective.
Mhm.
And somehow the degenerations are still controlled by trees. So for those spaces, a similar formula holds.
Cool.
And then for the positive genus moduli spaces, it's not quite like plethistic inversion, but there is like a really nice formula due to Getzler and Kapranov that involves plethism,
Okay.
like relating everything on the open side to everything on the closed side. If that makes sense.
Yeah. Sort of. Cool. Thank you. Okay, I think we can thank you again, but I think we lost most of our audience over the course of the questions. But it was a really nice talk, and people stayed through the talk. I think it was just the questions that they.
Oh yeah, it's fine.